Hi, we're group A12 and we're going to be talking about random variable, expectation, and variance. First of all, you're going to look at the definition of expected value. Expected value is a weighted average of the values of a random variable. And I'm going to talk about random variables very briefly. So, a random variable over a sample space is a function that maps every sample point to a real number. And let me explain this through an example. So let's say we're rolling a dice and there are going to be 6 outcomes. So we're going to either get 1, 2, 3, 4, 5, 6, and we're going to assign a real number to each of the outcomes. And let's say let's assign number 1 to the outcome of getting 1, and 2 to getting outcome of 2, and 3, and so on. And to write this into more simple terms, let's say x equals 1 is x1, x equals 2 is x2, x equals 3 x3, and so on. So how do we find out the expected value? To find out the expected value, we have to add all elements in the sample space of the product of the probability of the element and the value of the random variable at this element. So if we write out an equation for this, it's going to be like expected value of a random variable x is equal to sum of all elements in the sample space of the product of probability of the element, which is p brackets s, and the value of the random variable at this element, which we'll say as x of s. And that is how we get expected value. If we write this out, expected value is said to be linear, which means that expected value of the sum of random variables is equal to the sum of their expected values, which is going to be expected value of x1 plus expected value of x2, and so on. So in summary, we are saying that expected value of the sum of random variables is the sum of the individual expected values. And the next thing I'm going to talk about is variance. So the variance is how spread out the values of random variables are. We are going to talk about this only briefly here. So the importance of knowing variance is that when we look at a graph with a graph showing how much probability is associated with each outcome. So for example, if we have a random distribution like this, so we want to know which range or how much probability we have for getting each outcome, and variance is very useful in figuring this kind of information out. And next we are going to Lyndon is going to talk about linearity of expectations, and he's gonna prove that.
Okay, so like we mentioned, the expected value of x1 plus x2 till xn equals the expected value of the individual, like expected value of x1 plus expected value of x2, so on, so forth. Oops. So I'm going to try to prove that. So to start out with, I'm going to say the expected value of 1 plus x1 plus x2 equals the sum of the probability times x1 plus x2. So going on one more step, if I multiply it out within the sums, I will get probability times x1 plus the sum of probability times x2. So, and if you look at this, this equals the expected value of x1, and this is the expected value of x2. So there you have it. Expected value of x1 plus x2 equals the expected value of x1 plus expected value of x2. Now, the second theorem that I'm going to prove is expected value of ax plus b equals a times expected value of x plus b. I'm going to use a similar technique to prove this. So if I write out this equation in sum form and presume a and b are constants, so and x is a random variable. So if I write this out, I will get the sum of probability times ax plus b, and if I multiply it out like last time, I will get the sum of the probability times x times all right. Oh my gosh. Okay. Times a plus the sum of the probability times b. So this gives us expected value of x, and it tags along with a. So expected value of x times a plus this. Since we know that the sum of probability s equals 1, because the sum of any probability will always equal 1, and I will get 1 times b. Thus, it proves that expected value of ax plus b equals a times expected value of x plus b. Now, Connor will get more examples on expected values.
Alright, so I'm going to give a couple of examples of how we can apply the first theorem to some real-life situations. For the first example, we're going to find the expected value of the sum of two dice. We're going to let x represent x be the random variable that represents the sum of the two dice, x1 and x2 be the random variables that represent the individual rolls. Since both dice or both die are the same, and each possibility or each outcome has an equal possibility of occurring, we can find the expected value, or the expected value for each die are going to be equal. And to find that, we multiply the outcomes times their probability, and since each outcome has the same probability, we just add the total number of possible outcomes and divide it by the probability, which is 1/6. Or, yeah, divided by the probability, 1/6. And this equals 21/6, which equals 7/2. From the linearity of expectations, we know that the expected value of the sum of the two dice equals the sum of the expected values of the individual die, which equals 7/2 plus 7/2, which equals 7. And this result makes sense because there are more unique ways to roll a 7 than any other possible value. For the second example, a new employee checks the hats of n people at a restaurant, forgetting to put claim check numbers on the hats. When customers return for their hats, the checker gives them back hats randomly. What is the expected number of hats that are returned correctly? So we have n people, and we're going to let x represent the number of people who receive the correct hat, and we're going to let xi be the random variable that the ith person receives the correct hat. And xi is going to equal 1 if they are given the correct hat, or 0 otherwise. Since we have n people, but there is only one correct hat for each person, the probability that the person receives the correct hat is just 1 over n. Therefore, the expected value that an individual person receives the correct hat is the outcome 1 times the probability plus 0 times the probability that they do not receive the correct hat. And this just equals 1 times 1 over n. So that equals 1 over n. To find the expected value of the total number of people who receive the correct hat, we just add the expected value that each individual person receives the correct hat. Since there are n number of people and the expected value that each person receives the correct hat is 1 over n, we have m times 1 over n, which just equals 1. This is an interesting result because it does not depend on n. So no matter how many people check in their hat, the expected number of people who receive the correct hat back is 1. Thank you for listening to our presentation.